Welcome back. So far, we've learned that a note on pretty much any instrument produces many different frequencies. We call these overtones or harmonics. It's a symphony in a single note. We've learned how much of each overtone is produced is called timbre. And we've learned to break down a waveform into its constituent frequencies, sort of figuring out what recipe goes with a particular sound. The mathematics of that is the Fourier transform. And your ear does that. Your bodies actually take a Fourier transform when you listen to things. Today, we're going to figure out how these ideas lead to our brains being tricked. These are called auditory illusions. We're also going to learn how pitch, how we talk about it, and why it's not so simple as a sort of a low to high continuum. And we're going to find out how auditory illusions are used in music. Oh, I'm sorry. Oh, it's the producer. I really have to take this. Hello?
Hey Dave, not everyone's familiar with the term auditory illusion. You should define it.
Oh, that's a really good point. I'll get to it. Sorry about that. Well, an auditory illusion is, well, actually, you just heard one. You see, that was the producer. Could you tell if the producer was male or female? Now, that's probably really easy for you. As a male producer, you heard the nice low frequencies of Zach's male voice, right? Actually, you didn't hear the low frequencies of Zach's voice. It was an auditory illusion. Your brain is tricking you into thinking something is there when it really isn't. An auditory illusion is a lot like an optical illusion. Optical illusions are visual things that trick your brain. Auditory illusions are sounds that trick your brain. The basic conundrum is like this. A man's voice vibrates at maybe around 100 hertz. A woman's voice is much higher, maybe 350 hertz or so. The speaker on a cell phone only has a range of about 350 hertz up to 4,000 hertz. Your brain thinks you hear the low frequencies of Zach's voice, but the speaker on the cell phone simply can't produce frequencies that low. It's missing the fundamental in the first couple of overtones. Why is your brain tricked? Why don't you think all callers are women? It's because you have knowledge of overtones and the Fourier transform and how our ear works. We're going to use that knowledge to figure out exactly what happens. So let's quickly go through what exactly happens when Zach calls and we talk to him on the phone. Now this is a bit of a simplification, but, well, here's Zach's voice again.
Auditory illusion.
When Zach speaks like that, the vibrations are not just at 100 hertz, but also overtones. Vocal cords, like all of the other one-dimensional vibrators we've talked about, vibrate at a particular sequence of overtones, the harmonic series. And so when you hear something at 100 hertz, his vocal cords are also vibrating at 200 hertz, 300 hertz, 400 hertz, 500, 600, 700, on and on up that series. When he speaks, those vibrations are digitally encoded by his phone and then sent, zeros and ones. That message is sent to my phone, and the waveform is decoded by my phone. Now at this point, we're still not missing the fundamental in the first few overtones. The entire signal is there. It's when it's played back on my phone speaker that we lose some of the lower overtones. The range is from 350 to 4,000 hertz, and so the speaker only plays things like 400 hertz, 500, 600, 700, 800. It's missing the lowest, the 100, 200, and 300. And here's where your brain gets involved. Your ear, first of all, does the Fourier transform, and it sends the spectrum to the brain. And we're going to talk a little bit more about how your brain does this in lecture 12. But your brain essentially is an absolutely fantastic pattern recognition machine. And your brain asks, well, is the sound of a voice at a high G? Because after all, 400 hertz is the lowest frequency that's being transmitted to your ear. And your brain does the following thinking. If it were a 400 hertz sound, then the overtones would be 800, 1200, 16. It would be multiples of 400. But the sound that you're hearing also has 500, 600, 700. It has the 800, but it also has 900, 1000, 1100. In fact, 3/4 of the sounds that are coming to your brain don't fit the pattern. And so your brain rules out the possibility that it's a 400 hertz note. On the other hand, is the sound a voice at a low G a 100 hertz note? That's actually closer. That pattern matches closer to what your brain knows as a 100 hertz note. A 100 hertz note would vibrate at 100, 200, 300, 400, 500, 600, and all you're missing in that is the first three, 100, 200, and 300. This is actually a neurological phenomenon. What's going on in your brain? In your brain, the idea of a low G means a particular set of neurons all firing at the same time. When you hear a 100 hertz note, when something vibrates at 100 hertz, there's actually a neuron. The neuroscientists can tell now that there's a neuron that's vibrating, that's firing 100 times per second. And when there's something vibrating at 200 times per second, there's another neuron that's firing at exactly 200 hertz per second, and 300 and 400 and 500 and 600. And so the idea of a low G is simply a whole set of neurons all firing at the same time. And when you remove just 3 of those, you're still firing nearly the same set of neurons. To your brain, the pitch low G is just a particular pattern of neurons firing together. And when Zach talks to us on the phone, his phone voice doesn't fit that pattern perfectly, but it fits close enough. You hear a low G, you hear a man's voice, even though the low frequencies aren't there. Now we have to remember in this discussion the difference between pitch and frequency. Now both relate to how high or how low a note is, the bass versus the soprano. But pitch is the perceptual attribute. More particularly, you might call it the psychoacoustical attribute of a sound, whereas frequency is the physical attribute of the waveform. The missing fundamental tells us that pitch and frequency are not the same. When Zach speaks at 100 hertz, the pitch is a low G, but what comes through on the phone, the lowest frequency is 400 hertz. Now in most cases, pitch and frequency are really interchangeable, and we think of them as the same thing. In fact, usually when I'm speaking to a musical audience, I'll talk about pitch, and when I'm talking to more of a math or science audience, I'll talk about frequency. But really, we should be more particular, and when we're talking about perceptual things, use the word pitch, and talking about physical vibrations, we should use the word frequency. This distinction between perceptual attributes and physical attributes is actually the source of something you've probably heard before. If a tree falls in the woods and no one's there to hear it, does it make a sound? Well, the definition of sound is that sound is a perceptual attribute, not a physical attribute. And therefore, when a tree falls in the woods, if a tree falls and no one's there to hear it, there is no sound because nobody is perceiving it. The lack of perception means there is no sound. So let's dig deeper into this and try to understand what's going on musically. We're going to need a lot more music in later lectures, and so we're going to talk about some notation here. Now I know this is going to be a review for some of you, and this might be a little bit too quick for others. So if this is too quick for you, you might need to replay this section, especially if you're new to music. I've found that for most students, the easiest point of entry is a piano keyboard with its lovely ebony and ivory keys. So let's look at a piano keyboard. On a piano keyboard, the higher pitches are to the right and the lower pitches are to the left. The white keys are named, and they're named A, B, C, D, E, all the way through G, and then that pattern repeats, A, B, C, again and again. You need some place to start, and the sort of reference place on a piano is 440 hertz, and that is A. Now there's a long story. The reference point has not always been 440 hertz. It's gone back and forth. In fact, modern orchestras typically tune a little bit sharp because it sounds a little bit happier. But for now, the reference point is 440 hertz. So that's the names of the white keys. The black keys are the sharps and the flats, the incidentals. The black key between A and B is A sharp, and it's also named B flat. And at least on a piano, those are the same. We'll find out later that those really shouldn't be the same, but that's for another lecture. The interval between two notes is how far in pitch to go from the lower one to the higher one. The smallest interval we have, the smallest interval on a piano is to go from one key to the next, black or white, or from white to white. And so a half step is what we call that. Going from A to A sharp would be a half step, going from G flat to G would be a half step, and going between the two white keys, B and C, is also a half step. Going from one key to the next of the same name is called an octave. So going from an A to another A, the next A, or going from a D sharp to the next D sharp, that's called an octave. And if we need to distinguish A's, since there are many different A's, we put numbers on them. So A0 is the very lowest A on the piano, and then A1, A2, A3. It's actually A4 that's a 440 hertz. Now, there's a bit of an oddity about this. You increase the number not at A, like you think you might, but at C. And so the bottommost notes are A0, B0, and then C1. And if you were to go up to 440A, that's A4, and then B4, and then C5. Now a sharp symbol means to go up one half step, and that really just means to go up one key on the piano, and a flat symbol means to go down one. So a B sharp is actually the same thing as a C. And an F flat is the same thing as an E. And we can actually do double sharps and double flats. Some composers love to use those. They're making it very difficult to read music. But a B double sharp is the same thing as a C sharp. And an F double flat is the same thing as an E flat, at least on a piano. An octave is made up of 12 half steps. If you start at one name and go up 12 keys, you'll get to another key of the same name. So how do these notes correspond to frequencies? If you look at the A's, the octaves above and below 440 hertz, you can ask, what are the frequencies of those notes? Now going up, you start at 440 hertz, and then the next A is at 880, and the next one is at 1760. You have to double the frequency every time you go up an octave. You notice we're not just adding 440 hertz each time. To go down from an A, a 440A, you halve it, so you get 220, and then 110 hertz, and then 55. To go up an octave, you multiply by 2. To go down an octave, you divide by 2. The key observation here is that octaves are multiplicative. Remember that overtones are additive. This difference between this multiplicative system of intervals and an additive system of overtones has incredible numbers of implications. And some of them are very surprising. One of them we're going to talk about today, and that's the fact that no piano is ever in tune. More about that later. I do want to make sure we understand the difference between an additive system and a multiplicative system. So suppose a piano key sounds at some fundamental frequency. Let's just call it X. We can ask, what are the octaves above and below X? What are the frequencies of those? Well, above, you would multiply by 2. And so the octaves above X would be 2X, 4X, 8X, 16X. And going back down the other way, we would have 1/2 X, 1/4 X, and 1/8 X. In general, if you want to go n octaves away from X, the formula would be 2 to the n X. And that actually works for both positive and negative n. To get from one to the next, we multiply. And the general formula here is exponential. It's 2 to the n X. N is an exponent, and really what we're doing here is repeated multiplication is exactly what exponentiation is. What about the overtones? Let's go back to this frequency X that we're playing a piano key at. What are the harmonics, the overtones that you would hear? We talked about those before, and those exactly are the multiples. 2x, 3x, 4x, 5x, 6x, 7x. And in general, the nth harmonic above x is going to be nx. There is this discrepancy in naming. The nth overtone is actually n plus 1 times x because of this discrepancy. Now, we should note that that works only for positive n. There are no harmonics below the fundamental, at least in natural sounds. To get from one to the next, we're just adding x again. And the general formula here has n times x. And it's multiplication because multiplication is just repeated addition. So let's compare these two. We have the overtones and we have the octaves. And we're playing a frequency x. We're also going to hear the overtones, x, 2x, 3x, 4x, 5x. And the octaves above that are x, 2x, 4x, 8x, 16x. All of the octaves are in the overtone series, but not all of the notes in the overtone series are octaves. It's a little bit like the fact that every square is a rectangle, but not every rectangle is a square. When you hear a 100 hertz note, many of the overtones you hear are octaves. What about the overtones that aren't octaves? Now, this is going to be necessary for later discussions of scale, so we should get into this now. And we're going to use digital technology in order to hear this. So I'm going to play a G repeatedly. It's not exactly at 200 hertz, but for the simplifications of the calculations, let's call it 200 hertz. And Gordy, our sound engineer, is going to isolate each overtone in turn. So I'm going to play the full G like this. And now what he's going to do is he's going to isolate each one of these in turn. So here is just the fundamental. Even though I'm playing it, you're only going to hear the fundamental. And that's a G3. And now here's the first overtone, the second harmonic. K equals 2 if you're working with the formula. It's at 400 hertz. Now, if you find that on a piano, you notice that that's exactly 1 octave above the fundamental. And so that one is a G4. Here's the third harmonic. We're now at 600 hertz. I'm still playing the G, and you're going to hear the third harmonic. You'll notice that that's not a G anymore. Musically, that's a D, and it's a D5. And what mode you're hearing is you're hearing the mode where the jump rope is divided into 3 pieces with 2 nodes. Here's the 4th harmonic at 800 hertz. And it shouldn't be surprising that that's a G again, because we've doubled the 400 hertz we heard a minute ago. Here's the 5th harmonic. We're now at 1000 hertz. And the note you're hearing now is a B5 if you find it on a piano. So let's look at multiple representations of these harmonics. Now, mathematicians love to look at different representations. Mathematicians have things like algebraic representations, graphical, numerical, verbal representations. I like to think of it sort of like Hokusai's famous woodblock prints, 36 Views of Mount Fuji. The most famous is probably the Great Wave off Kanagawa. Hokusai was looking at the same subject, Mount Fuji in his case, from different perspectives. Mathematicians do this. They might take something like a parabola, y equals x squared, and look at it from an algebraic perspective or a graphical or even a numerical perspective with a table of numbers. And experts in mathematics effortlessly translate between these 2 representations, between any one of these, picking the most useful one for their purposes at the particular time. Different representations of a musical note are also important, and we have many of them. We have the sound. You could hear a musical note, whether it's the original sound or digitally modified like we just heard. There are numbers involved, the frequencies, or in fact the wavelengths. You could think of these as keys on a piano representing those notes. You could think of them as notes on a staff, how we read music. You could even think of them in terms of the spectrum, and look at the spectrum and look at the different peaks. Each one of those peaks is a different frequency using the Fourier transform. Now, expert musicians and people who deal with sound a lot effortlessly translate among these different representations. So let's look at the harmonics of an F2. Now, an F2 is about 87 hertz. A full F2 on a piano, it's too low for my violin, so I can't play it, but here's an F2 on a piano. And it might be too low for your speakers, but you're still going to hear it because of the missing fundamental illusion. We're going to play the sequence of overtones of F2, all the first 10 of them. And every time we're going to add a different representation so that you get a sense of how these representations work together. Now, I want to tell you that there's an important thing about sine waves versus notes. If we use just sine waves, then these lowest notes at 87 hertz, your speaker might not be able to play it and you wouldn't hear anything. Instead, we're going to use notes with overtones. We're going to generate these with a computer, but we're going to use notes with overtones. And because we do that, even though your speaker can't play at 87 hertz, you're going to hear all the overtones, and you're going to know that we're playing a note at 87 hertz. So let's begin with sound. So here's an F2 with all of its overtones in turn. And now let's add the frequencies, the numbers, the representation that involves numbers. Here it is again, now with the numbers. And if you're quick with numbers, you notice that those are just the multiples of 87. Now let's look at this on a piano keyboard. Let's hear it again. Now you may remember that the 7th one, the 7th harmonic, is not on our scale. We're just pointing to a key that's the closest key that we have on that scale. Finally, we can look at notes on a musical staff. So let's play them again and look at the notes on the musical staff. And again, that 7th one, we don't have a way of representing that on our musical scale, so that's an approximation. What do we notice in all of these representations? Well, we notice that the octaves fall on the powers of 2. We've already discussed that. 1, 2, 4, 8. We've noticed that the 3rd harmonic is a C. That's the first note that isn't an F. It's the first note that isn't in the octave scale. And the C is a 5th above F. In other words, C is the 5th note on the F major scale. That's how it gets the name the 5th. For us, the two most important intervals are octaves, going from one note to the next of the same name, and the fifth note on the major scale of the lower note. Another way to think of a fifth is going up 7 half steps. Now there's a key mathematical observation that going up an octave is multiplying the frequency by 2, going down an octave is dividing by 2, and going up a fifth is multiplying the frequency by 3 halves, and therefore going down is dividing by 3 halves. Just to see that, let's look through a numerical example to make sure we understand this. The fundamental we're working with is 87 hertz. The second harmonic is going to be double that, 174, and the third harmonic is going to be another 87 hertz higher, 261. The notes, the fundamental is an F2, the second harmonic is an F3, and the third harmonic is a C4, 7 half steps above the F3. To go from one octave to the next, to go from F2 to F3, we're multiplying by 2. 87 hertz times 2 is equal to 174 hertz. To go from the F3 to the C4, that's a fifth again, we're multiplying by 3 halves. If you take 174 hertz and multiply by 3 halves, you get 261 hertz. In general, we see that this works exactly. Octaves are multiplying by 2, fifths are multiplying by 3 halves. If we were talking about wavelengths instead of frequencies, going up an octave would be dividing by 2, and going up a fifth would be dividing by 3 halves, because remember, there's this reciprocal relationship between frequencies and wavelengths. Now there's an important complicating factor, especially if we're thinking about playing this on a piano. If we're looking at the F2, the first overtone, the second harmonic above an F2 is an F3. But if we play an F3 on a piano, we hear its overtones. And the overtone series of an F3 is not necessarily the same thing as the overtone series of an F2. The third harmonic above the F2 is C4, but when we play a C4 on a piano, we hear its overtone series. Each note comes with its own symphony of overtones. And when we play two notes, if those overtones match up, it sort of gives us a pleasant sound. Musicians call this consonance. And if the overtones don't match up, it gives us a sort of unpleasant sound, and musicians call this dissonance. We're going to talk much more about this in later lectures. I want to take us on a quick mathematical tangent, though. Did you notice how the overtones kept getting closer together as we went up the piano keyboard? There's a mathematical reason for this. The intervals are multiplicative. If you go from one octave to the next, you're multiplying by 2. The normal number line has equally spaced points. If you remember a normal number line from when you were young, it's 1 to 2 and then 2 to 3. Each one of those had the same space. Equally spaced points, the differences were the same. On a keyboard, equally spaced intervals on a keyboard don't have that. It's the ratios that are the same, not the differences that are the same. Mathematicians hear this and think of a logarithmic scale. And logarithmic scales come up in many different areas. If you look at investments, the proper scale to look at investments is on a logarithmic scale. You can double your money, and then you double it again, and we should be looking at the same thing in terms of investments. A Richter scale used to measure earthquake severity, that's also a logarithmic scale. If you go from a 6.0 on the Richter scale to an earthquake that's 7.0, it's actually 10 times worse in terms of the amplitude of the vibration. And if you go from a 7.0 to an 8.0, the 8.0 versus the 6.0 is now 100 times worse in terms of that vibration. Decibels are another example of a logarithmic scale, and that's something we've seen before. Going up 10 decibels means you've increased the intensity of the sound by a factor of 10. And every time you go up 10 decibels, it's another factor of 10. The keyboard here is a physical example of a logarithmic scale, where every time you go up, you're multiplying and not adding. So let's go back and see if we can deconstruct the missing fundamental now that we know some more information about intervals and notes and pitch. The basic idea here is that when you remove the lower overtones, your brain reconstructs the fundamental and it fools you. And let's see if we can hear that musically this time on my violin. So each time I play a G3, right around 200 hertz, Gordy's going to remove the next lowest frequency. And as he removes overtones, the timbre is going to change. But because of this missing fundamental illusion, Musicians are all going to agree that the fundamental stays at G3, even though there are no frequencies that low anymore. So I'm just going to keep playing G3s. Each time, Gordy's going to remove the next lower overtone. Here's the full G3, first of all. And now we're going to start removing overtones. And what you can hear is it gets tinier and tinier, but the fundamental stays at the same pitch. It's still a G3. Now, instead of removing overtones, let's try to add them. And so we're going to add up overtones. Here we're actually making the recipe. We're using the recipe and putting things in. And we're going to start with just the second harmonic. We're going to completely remove the fundamental and all of the higher ones and just let you listen to the second harmonic. And that should sound an octave above. For reference, the G that I'm going to play, here's the full G. And the pitch of the octave above, the second harmonic, is an octave above that. And that's a G4. So we're going to start by playing just that second harmonic, and then we're going to add the third, add the fourth, and gradually, as we add the higher harmonics, you get a bigger, a more complete picture of the sound, and gradually you're going to actually start to hear the fundamental, which is lower, down at G3. So here we go. And again, even though you're not hearing anything vibrating at 200 hertz, you gradually start to perceive a note that low. We're adding the higher frequencies, and at some point your brain starts reconstructing the lower one. Let's hear that one more time so you get a sense of this. So how is this used in music? It turns out that organ makers use this auditory illusion. The lowest note needed in organ music, most of the time, is a note that's incredibly low. It's at 16.4 hertz. And to produce a note that low, you have to have a 32-foot pipe. Now the problem is that many churches are simply too small to fit a 32-foot pipe. The solution is to use the missing fundamental illusion to make people think that there's a 32-foot pipe there. We're doing what we just did. We're adding higher frequencies to get the illusion of a lower one. A 32-foot pipe vibrates at 16.4 hertz. Let's just call that X so we don't have to deal with the numbers. The overtones of a correct 32-foot pipe should be 2X, 3X, 4X, 5X, 6X, on and on up. Now you can't fit that 32-foot pipe, but you can fit smaller pipes. And now let's figure out which smaller pipes you should put. The idea here is to produce the first and second overtones of what would be a 32-foot pipe so that listeners will hear the fundamental. So we need to figure out what pipe would have a fundamental of 2X. And when we do that, we figure out that it's a 16-foot pipe. It's exactly half the length. The wavelength is half so that the frequency is doubled. And so we put a 16-foot pipe, so the fundamental of the 16-foot pipe is at 2X. But that's only going to produce overtones at 2X, 4X, 6X, 8X, 10, 12. Those are going to be the overtones of a 16-foot pipe. In particular, we're missing 3X, so let's put another pipe with a fundamental of 3X. And when you think about that, we're trying to triple the frequency, and so we should take the wavelength and cut it by a factor of 1/3. And that's the size pipe you need. You need, well, 32 feet divided by 3 gives you a 10 2/3 foot pipe. And when you put a 10 2/3 foot pipe in there, you hear the overtones of that, which are going to be the fundamental at 3X and then its overtones at 6X, 9X, 12X, 15, just the multiples of 3X. When we put all of these together, if we play the 16-foot pipe and the 10 2/3 foot pipe, and we listen to all of those overtones, the things that we're hearing are 2X, 3X, 4X, 6X, 8X, 9X, 10X, 12X. We're only missing a few of them. We're missing 7X, 11x. And so we're only missing a few of them, and that gives us the illusion of something playing at x hertz. Now, most churches can accommodate 10-foot and 16-foot pipes, and so the problem is solved. So let's try to hear this effect. We're going to play some organ music in the background, and the missing fundamental illusion here is actually happening on two different levels. Now, the organ might be tricking you into thinking it has a 32-foot pipe when it doesn't. I'm actually not sure which church and which organ this particular organ music was played on, but it might have not a 32-foot pipe, but the 10 2/3 and the 16-foot pipe. And so the organ itself might be tricking us. But if you don't have a nice sound system with some big subwoofer playing the very low frequencies, then your speakers probably can't produce the lowest notes even of the 10 2/3 and 16-foot pipe. It's multiple layers of illusions. Your brain is tricking you into hearing something that I'm telling you is your brain tricking you into hearing a long organ pipe. Oh, that hurt to think about. Let's move on to another sound illusion. Let's move on to the scale illusion. Now, your brain is an amazing pattern recognizer, and sometimes it gets fooled because of that. The scale illusion uses stereo sound to fool it. Now, this illusion will be better if you have headphones or a good stereo system, but the point will be clear without it. I'll make sure that you understand the point, even if you don't have those things. This isn't exactly mathematical, but it is a form of pattern recognition, which is very mathematical, and this effect is incredibly cool. This is work done by Diana Deutsch, who's a pioneer in psychoacoustics. She was British born, and she works at the University of California, San Diego. She has many, many different auditory illusions, and if you look on her website, you can hear these. We're going to listen to the full sound at first, and then we'll deconstruct it. Here's the full sound of the scale illusion. What did you hear when we listened to that? If you're like most people, what you heard was that in one ear, the sound went down and back up in pitch. Bum, 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 bum. In the other ear, it went up and back down. Bum, 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 bum. What was actually played? Let's take these apart and listen to the left and right tracks separately. In fact, there were no descending or ascending scales at all. It didn't go up and back down, it jumped around. Your brain was tricked. This is pattern recognition gone awry. You are so used to hearing scales that go up and back down that your brain mixed the sounds up and said, you must be hearing a scale. Now, Deutsch identified this illusion in 1973, but Tchaikovsky used it in 1893. So let's go and let's hear what Tchaikovsky did with this scale illusion. In the Sixth Symphony, which is titled Pathétique, which doesn't mean pathetic, it means something more like sympathetic. The Sixth Symphony is a little bit strange in terms of symphonic structure. It has a triumphant, fast third movement. Usually the last movement is fast and triumphant, but the last movement of the Pathétique is a slow, tragic movement. It was written just before his death, which might have been a suicide. Music historians are a little bit uncertain of this. One very prominent theory is that Tchaikovsky was gay and he was about to be outed, and instead of going through that, he drank unboiled water and he died of cholera just a few days later. The Pathétique was first performed just 9 days before his death, and the scale illusion comes in the opening of the last movement. Here's the opening theme. I'll play it for you on my violin first. It's such an emotive melody. I have vivid memories of the first time I played the symphony. I was at Interlochen Music Camp for the summer, and we were playing with Carl St. Clair, who conducted the Boston Symphony sometimes. He's now at the Pacific Symphony. And we played it the first time without much emotion at all. And St. Clair stopped the orchestra and said, Tchaikovsky wrote 3 ballets, 10 operas, 6 symphonies, wonderful concertos. He wrote some of the best music ever written. And these are some of the last notes Tchaikovsky ever wrote. He knew he was going to die. Let's play that again. And indeed, we played that theme with much more emotion. Or did we? We certainly played with much more emotion, and it sounded much better, but we didn't actually play the theme. None of us played the theme, because the theme is actually an illusion. In order to see that, let's look at the score, because this mournful, this disconsolate melody isn't actually there. Now, if you can't read music, it's okay. We'll help you get through this. We'll give you the gist of this. Here are the first and second violin parts. In an orchestra, the first violin part is a group, probably about 16 violins, and they're playing one part. And the second violin part is played by maybe 14 violinists. They're separate sections playing different music. So here's what the first violins are playing. That's the first violin part. Here's what the second violins are playing. The mournful melody actually emerges from both parts. It's the scale illusion. So let me play the melody that you hear, and we'll highlight one note at each time, how you're hearing this melody. Now that was just my violin. Let's hear it with the entire symphony the way it was meant to be heard. So here's the passage with the entire symphony, and I hope you can hear the melody as it comes out that's not really there. It's just the individual parts coming together with this scale illusion. Here's Tchaikovsky's Sixth Symphony, the opening. It's such a wonderful piece to listen to. Just to make sure we understand, here again I'll play the individual parts, the part you can't hear because nobody is playing the actual melody. Here's the first violin part. And here's what the second violins are playing. And those two are working together to give us the illusion of this wonderful, beautiful melody. Finally, we're going to talk about three stranger illusions that really bend the mind a little bit. We're going to talk about shepherd tones, falling bells, and the tritone paradox. Let's look at shepherd tones first, and there's actually no better way to introduce you to shepherd tones than just to let you listen. Here's a continuous version of shepherd tones. And here's a discrete. That's the mathematical word for sort of separate, individual version. These sounds might be reminiscent of an optical illusion, the Penrose staircase. You've probably seen something like this in the work of M.C. Escher. Works like Waterfall or Ascending and Descending use this illusion. And like the staircase, shepherd tones are always going up, but somehow manage to get back where they started. So who is Roger Shepard of the shepherd tones? Roger Shepard was a cognitive scientist with a psychology PhD from Yale. He worked at Bell Labs and Harvard and Stanford. He's a recipient of the National Medal of Science. He really liked to find ways of tricking the brain. Some of them were optical. Shepard drawings are quite famous. But he's actually most famous for his auditory illusion, the endlessly rising tone. So let's see if we can understand what's going on with shepherd tones. How can you make an endlessly rising note? Well, the key is that each note is a symphony of different frequencies. So here's the basic idea. Imagine that you sit down at a piano and you play, let's do something easy first. Just an A and then A sharp and then B and then C, C sharp. By the time you get to the next A, you will have played all 12 notes and gotten to the A, and you will have definitely gone up exactly 1 octave. Now let's do something a little crazier. Let's sit down at an infinite keyboard that goes infinitely low and infinitely high. And let's sit down and play not just one A, but every single A on the keyboard, and then every single A sharp, and then every single B, C, C sharp. By the time we get up to A, you're playing the same note we started with because you're playing every single A on the piano. You're back to the beginning. At every stage, you're going up 1/2 step, but you manage to get back to the beginning. In other words, shepherd tones are actually in a circle. Now let's refine this just a little bit, because there's a problem with this. Because we only perceive notes as low as some particular value and as high as some other particular value, you might actually hear notes jumping into that if we did what I just suggested. And there's a solution to this, which is part of the shepherd tones, and that's to play the middle notes very loudly, and to play the higher octaves softer and softer, and to play the lower octaves softer and softer. It's to put these sounds in sort of an envelope. And now as we play the notes, boom, 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 instead of jumping into our range of hearing, the notes at the bottom creep in, so we don't hear something jumping down to our lowest range of hearing. And we don't hear things going out of our range of hearing because we're sort of creeping out of the range. Now, related to shepherd tones is an illusion called falling bells. And it's fairly easy to explain this once we have this idea of the shepherd tones encased in this sort of envelope. With just a small adjustment, we can understand falling bells. Falling bells are notes that seem to rise, but actually they don't just come back to where they started, they actually fall over time. The idea is to take shepherd tones, again we're just moving up, bum, 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 on our infinite piano, and now take this envelope in which they're encased and slowly move that envelope downward. Now from one note to the next, your pitch is definitely going up, but over time, the envelope drags the pitches lower and lower. If you want to hear this, it's on YouTube. It's a wonderful little illusion. Finally, let's go to the tritone paradox. Let's again listen to this illusion first. So what you're about to hear is 4 pairs of notes. And for each pair of notes, I want you to decide for yourself, is it going from a lower note to a higher note? Or is it going from a higher note to a lower note? On the piano, are you going from one note further to the right, or are you going from one note further to the left? If you're with somebody else, you might want to give thumbs up. When I do this for large crowds, I ask everybody to give a thumbs up if it's going from a lower note to a higher note, and a thumbs down if they think it's going from a higher note to a lower note. So let's hear that. It turns out that people disagree whether those are going from higher notes to lower notes. In fact, well-trained musicians disagree, and the funny thing is each one of them is sure of their answer. I've done this in audiences of 500 people, and there's thumbs going up and down all over the place, and people are arguing with each other. What's going on? When you hear these tritones, well, first of all, we should explain what a tritone is. A tritone is a musical term for a particular interval of 6 half steps. It goes from A to D sharp would be a tritone, or from C to F sharp. I can play them for you on a violin here. Here's a tritone. If we add one more note, you get a famous theme. You hear that in many places, but probably the most famous are Maria from West Side Story. It's also the intro to the Simpsons theme on TV. Now, to understand this paradox, all we're doing is we're taking those shepherd tones we had before, and we're playing 2 of them that are 6 half steps apart. 6 half steps is across the circle from this 12 notes that are on the circle that are the shepherd tones. Do you think the intervals go up? That means you're thinking you're going one way around that circle. If you think those notes are going down, you're just going down the other way around the circle. Which view is correct? Well, neither one, really. You see, when you go from playing every A on an infinite piano to every D sharp, you might have gone from every A up to a D sharp, or you might have gone from every A down 6 keys to a D sharp. Because it's every A and then every D sharp, those notes, you can't distinguish between those two things. You simply can't compare these two notes that we've played for you in this tritone illusion. Higher or lower, it's not really clear. Each note is made up of many different frequencies. You can compare two individual frequencies, but once we manufacture them and put them into these notes, you can't compare the entire note. Let's go back to the definition of timbre we saw before. In Lecture 2, we heard that timbre is more complex than pitch, because pitch can be represented on a one-dimensional scale, low to high. The Shepard tones and Deutsch's work show that it's not so simple. They've constructed notes that can't be compared in pitch. Neither is really higher nor lower than the other. Frequency, the physical, not the perceived attribute, is a one-dimensional scale, but pitch, the perceived attribute, is much more complicated. We might think that one note is higher than another, but in reality, they might not be comparable. Oh, I'm sorry. It's Zach again. But now we know something about men's voices on phones. Let's listen. Hey, Zach.
Dave, I know you love these, but we're out of time. No more auditory illusions.
Oh, okay. But now they know why they can tell that you're a guy.
There are easier ways.
Well, easier, yes, but now you know not only how the missing fundamental illusion tricks your brain when you're on the phone, but you also know how pitch is much more complicated than you might have first thought. You know how you can use overtones to construct sounds that trick your mind. For a musical coda, let's return to a piece of music with all of its frequencies intact. So I'm going to play for you the Arabian Dance from Tchaikovsky's Nutcracker Suite. The Arabian Dance is based on an Arabian scale, not the standard Western scale. And it's a good way to foreshadow what we're going to talk about in the next lecture. Next lecture's discussion is about the mathematics of different scales. Thanks for joining us.